In the next part of this chapter, we are going to look at how the graphs of modulus functions can be related to the graph of y equals to fx. So let's do a brief recap on the modulus function first. Recall that we first encountered this in the topic of graphs. So where this is the graph of y equals to x, what we have here is y equals to modulus x that is v-shaped in nature. And we pay attention to the fact that this region in the negative y region is actually reflected about the x-axis to yield positive y values. So the graph is consistent with what we know of the modulus function when we define it algebraically, because you have these two portions that correspond to different x values. Okay, so what do I mean by that? Where your x is greater than or equals to 0, there is actually no change in the graph, right? You look at this blue portion, because in this region of the graph, x is greater than or equals to 0. So we just sketch the y equals to x graph for this region x greater than or equals to 0. However, when it comes to this x less than 0 part, so that's this portion here, okay, where x is less than 0, what we have to do is multiply this negative 1 to the values of y, and that results in this reflection of the graph about the x-axis only for this portion. Okay, so that's why your graph looks like this. If you find this a little bit confusing, right, like why there is a negative sign here, what we can do is we try with some numerical examples. Meaning, if I take modulus of -5, intuitively I know that we are looking for a positive 5. But how do we invoke that positive 5? We do it by introducing this negative sign from the formula here and the original x value of -5. So overall, you get a positive 5. Okay, so this is actually what is going on with the modulus function. Now we are going to apply these ideas into the graph of y equals to fx. Okay, so for y equals to fx, modulus fx, so if we apply the modulus on the fx, then same thing, if my fx itself, if the input here, the fx, is greater than or equals to 0, we are going to retain that portion. That means we are not expecting to see any changes because the y values are positive to begin with, right? But if my y values are negative, then I need to have a negative fx, okay, to turn the negative into a positive. Good outlook in life, by the way. All right. So how does this work out in a graph? We look at this example of y equals to ln x. So the positive region, right, will stay the same because it's positive anyway. But this region that is in the negative y values, right, this portion will have to be reflected up. Okay, so where the y values are negative, we will reflect the graph about the x-axis. So if I were to just jump in on this negative sign and rewrite it, you will notice that this is relevant to what we have been doing for reflection. Because for the y equals to this negative fx, right? Actually, we have negative y equals to fx, correct? So I want you to consider like the original graph, right? Y equals to fx. Moving into this, you realize that we are replacing a y with a negative y, which is exactly this one, the reflection about the x-axis. Okay, so to summarize, when we want to sketch the graph of y equals to modulus fx, what we will do is we will retain the portion that is above the x-axis. This corresponds to this part of the definition that we encountered for the modulus. All right. And then for the region where the y values are negative, then we will proceed to reflect the portion that is below the x-axis. One final observation, whenever we are drawing the graph of modulus fx, we will expect to see that the outcome of this is a graph where all the y values are